Okay, so welcome everyone to a new academic year of VKC Talks. My name is Amy Maley, and I'm a master's student at UBC and the host of VKC. And I also have with me here Maya Kopilova, who's our convener. VKC is a series of seminars for diamond geology and related topics, and our goal is to bring academics and industry professionals together. I would first like to acknowledge SRK Consulting for being a long-standing VKC sponsor. And then just a few Zoom housekeeping notes before we get going here. Just make sure that your cameras and microphones are turned off during the duration of the presentation. And then the presentation is going to be about 50 minutes long. So if you could hold your questions until the end, and then I will help to facilitate a question and answer period at that time. Before we get started with today's talk, Barbara Scott-Smith is here, and she is going to say a few words about the 12th International Kimberlite Conference that's taking place next year. So, Barbara.
Thank you. I hope that most of you know that the 12th International Kimberlite Conference is happening next year in Yellowknife. There's only 7 months until the actual conference now. A lot's happened since our last VKC in May. And most importantly, the registration opened in July and is so far going quite well. The registration is open not only for the conferences, but also for the field trips. I'd then like to, because it's only 7 months away, the deadlines are starting to come. And if we could have the next slide, the next deadline is the 20th of December, which is only 3 weeks away. And that is for submission of short abstracts if you want to participate in the technical sessions. And we really hope you have something to say, and we'll submit it to make a good conference, as well as financial support for early career geologists mainly, but maybe other people might be able to get awarded funds. And we do have funds in place, so I'm supporting people applying, and that has to be again by the 20th of December. Otherwise, please keep yourself informed either via the website. There's a mailing list on the website where you get e-blasts of important information, as well as our social media. So we look forward to seeing you next year, I hope, and participating in the conference. Thanks, Amy.
Thank you, Barbara. So now I would like to welcome today's speaker, Dr. Thomas Gernon. Tom received his degree in geology at the University College of Dublin in 2004. He then went on to complete a PhD and a short postdoc with Steve Sparks on Kimberlite volcanology at the University of Bristol, where he worked on diamond mines in South Africa, Botswana, and the Canadian Arctic. From there, he was a lecturer at Trinity College Dublin from 2008 to 2009. Tom is currently at the University of Southampton, where he is a professor in earth science based in the UK's National Oceanography Centre, and is currently on secondment as a principal research fellow. So without further ado, I will hand things over to Tom.
Thank you very much, Amy. I'll just share my screen, hopefully. There we go. Hopefully you can see my slides. Excellent. Thank you, Amy, again, and thank you very much to Maya as well for the invite to speak to you at the VKC, which is a great honor. And I'm especially pleased to be presenting work that we recently published relating to what drives Kimberlite volcanism. And I'll try not to get too technical in how I describe the processes as I'm talking about this. As Amy mentioned, I did my PhD at Bristol working on more the volcanology of Kimberlite systems nearer the surface. And I remember spending a lot of time in quite remote places, as you do when you work on Kimberlites, from the center of the African deserts all the way up to the Arctic tundra, not far from Yellowknife, which was a really great memories. But one thing that I remember there was, as I was thinking about Kimberlites, being in these places, it gave me a lot of time to think about why Kimberlites are there in the first place. And for me, that was an unresolved problem. And reading lots and lots of papers and books about the topic, I felt that it was something that wasn't really adequately kind of discussed in papers. And so it's a problem that's bugged me for a while, and partly because when I did my PhD, Viva, when I was examined on my PhD, my examiner asked me, why didn't you sort out, what drives these eruptions in the first place? And I thought that was a little bit unfair, but it was also an adequate point in that he had picked up as an outsider that this was a sort of a unresolved problem. And I then parked that problem because I went to work on other things in the meantime. But over the years, I kind of started working on different problems and developing new techniques. And I realized actually it's a good time to now go back to that problem with these new techniques, because I think we can start to unpick some of these problems. And so I'm going to talk about this paper, which was in Nature in this year, relating to this work, which it wasn't an overnight project. It was something that was a bit more organic, and it was something I chipped away at for a few years. But certainly it was something that was planted in my mind about 20 years ago while I was working in Africa. In fact, not far from this mine. This is the Gernon mine. Quite a long time ago. Sorry, there's a little bit of sound interference coming. This is the Gernon mine, and I'm sure you will know lots of kimberlites are formed in these pipes, these volcanic pipes, which are about 1 or 2 kilometers deep, typically. And this is the classic figure from Roger Mitchell's textbook. And you can see in the background, the kimberlite here is the green rock, and you can see there's a very sharp contact there where those white lines are, which represents the sides of one of these kimberlite pipes. And so what these mines do is allow us to access the sort of inner parts of the kimberlite volcanoes called the diatreme facies. And these rocks here are, they kind of look like the rocks here on the left, although these are from a different mine. These are from Venetia mine in South Africa. And when you look at these rocks, I think what's instantly recognizable is that they look a little bit like concrete in that they are very well mixed. They have a huge range of different class types, compositions, all these different rocks here, which are ripped from the sides as these pipes excavate from these volcanic explosions. And so it blasts lots of rock out of the ground and mixes it all up with the kimberlite itself, which of course contains the diamonds. And these darker crystals here are olivines, which have been altered over the time since they've been erupted. And on the right, of course, instantly recognizable is a nice Mackel twin diamond, which I actually found in Snap Lake diamond mine when I was working underground there. So I remember doing my health and safety induction of all things and seeing this little light reflect back from my torch underground from a little stream. And I knew instantly from the shape what it was. And it was my first time finding and picking up a stone, which unfortunately was whipped away by security. So I didn't get a chance to keep a souvenir of my trip there. But kimberlites, what I'm going to do in this talk, I'm not going to go straight into the work we did. I think it's important to sort of introduce some of the concepts here. So one of the concepts is where kimberlites are found. So they tend to be found generally in very stable cratonic regions. So these are really thick parts of the Earth's lithosphere or crust. And examples include, obviously, more or less what you are up in Canada, as well as Southern Africa, Southern America, and of course Siberia and Australia. And these diamonds, the kimberlites, I should say, tend to form in areas where the lithosphere is rather thick. And so to demonstrate that point, we have used some global reference models here for lithosphere thickness. And we've point sampled the thickness of the lithosphere for the most recent kimberlites in Sebastian Tapp's compilation, which is from 250 million years to the present. And when we use the most recent lithospheric model here, litho-ref18, we can see that the vast majority of kimberlites have a depth, lithospheric thickness corresponding to in and around about 170 kilometers thick, which is an important observation. The other observation about kimberlites, those of you who work on them will know that they tend to form not on their own, although they can. More likely that they form as part of clusters. So we have lots of kimberlites occurring in a field. And this map of Botswana here on the left shows quite nicely the scale of some of these fields. For example, Jwaneng, which I showed you earlier on, and Orapa, places I've worked. And you can see the scale bar shows you that these clusters are typically between 50 and 100 kilometers in diameter. And this is a nice example, the Kimberley cluster as well, where you can see there are kimberlites kind of along kind of a linear trend, although there are some off that trend as well. That's an important observation, the scale of kimberlite clusters. And the other one is that the Kelly Russell and colleagues have proposed that this kind of, I guess it's a consistency of scale that you get in kimberlite clusters. Obviously, there's variation about a certain trend, but on the whole, it suggests the kimberlite melt sources may have a scale of 10 to 100 kilometers as well. And that's a really useful constraint, I guess, to have when thinking about what it is that actually drives kimberlites, which was the elephant in the room I talked about earlier on. So the other observations about kimberlites relate to the times that we get them, in Earth history. And so if we zoom right out and think about deep time, this plot here on the top left shows you time from going from the Archean on the left, 2,500 million years ago, to zero on the present, zero on the right, which is the present. And you can see these peaks in kimberlites shown in green here. And these peaks, interestingly, seem to follow the tenure of great supercontinents, assembled landmasses in Earth history. So an example would be Columbia, about a billion or more years ago. Rodinia, which started breaking up about 800 million years ago. And of course, Pangaea, which you'll be familiar with, where Africa and, for example, South America separated starting in the sort of Jurassic Cretaceous period. So these peaks and kimberlites seem to follow the breakup or disaggregation of these united landmasses. That's important. And this isn't a new observation. Many people have pointed this out in papers going back a long way. For a really good summary on the topic, there's a great paper by Helsma et al. In the Lithos from the Kimberlite conference in 2008 or 9. And they proposed that the kimberlites are forming because of a fundamental change in plate stresses related to the breakup and reorganization of the plates as well on the Earth's surface. And this may be due to like far field stresses. So if you see on the map, this is a map here of southern Africa. You can see there's lots of fractures of all ages running through it. And what they're suggesting is when you open up a new ocean basin in the Atlantic, for example, you will have far field stresses being kind of communicated along these complex fraction networks. And a slight problem, I guess, with that model is that we know that some kimberlites don't necessarily travel along these major fraction networks, but also the lithosphere, the main part of the continent, the roots of the continent, is very strong. I mean, there's a reason why cratons are so long-lived in Earth history. They've been around a very long time. They've got lots of baggage, but they're very strong and stable. And so it's very hard to form a fracture that propagates through the lithosphere. It's nearly impossible to do that. So we do require some special kind of mechanism if this model is correct. And the other major model, I guess, to propose has been proposed by Torsvik et al. Is that the kimberlites are related to large low shear velocity provinces, which are basically major upwellings of the mantle. There are two on the planet in the Pacific and beneath Africa, shown as these red zones on this map. And you can see that the large igneous provinces, which Torsvik propose are fed by these big upwellings of mantle, form this kind of circle or this ring within which we tend to have most of the kimberlites. When you reconstruct this, you can see most kimberlites fall within this ring of large igneous provinces. So that's led them to propose that these are connected. Basically, your plumes are in some way seeding the base of the lithosphere or maybe heating it up and melting stuff and providing the melts that we need for kimberlites. And Steve Foley and people also proposed that these plumes may fertilize and possibly even destabilize the roots of cratons. And by that, I mean that these may provide fluids which give us the ingredients that are needed for kimberlite and possibly even diamond formation. Just another, I guess, seminal kind of picture of the world, of the Earth in cross-section here on the left from Giuliani and Pearson elements, 2019. They show the 4 scenarios in which we may form, diamonds, and they can be related, these kimberlite melts related to partial melting in the lower mantle or transition zone. They can be due to deep subduction. This is when the seafloor gets shoved down into the Earth's mantle, and this is depth beneath the surface here on the right. They can be due to partial melting at the lithosphere-asthenosphere boundary. This is the layer or the contact, I guess, between the continent and the asthenosphere or the mantle below it. And also they proposed partial melting in the upper asthenosphere, whereby there may or may not be a contribution from mantle upwelling. And that's shown nicely on the right. This is a plot here, or a diagram, I should say, from Steve Foley's 2007 paper, showing that the kind of conceptual view where plumes may provide, some hydrous ultramafic assemblages that kind of impregnate the roots of the cratonic mantle lithosphere. And they show many scenarios, but one of them is that you get delamination maybe of these blocks of the base of the lithosphere, and that may lead to erosion of the lithospheric roots, giving us a very irregular boundary at the base of the continent. And of course, that may also lead to small-scale convection in the mantle, because it's kind of an obstacle for any flow that you have or convection that you have in the underlying mantle. Just before moving on, this is a diagram from Graham Pearson's 2021 paper on cratons. And it's actually showing a section, the top here is showing a section through northern Canada, from the Slave through to the Sverdrup Basin. I'll probably not pronounce that correctly. But you can see what's interesting is that you can see that the lithosphere here thickens away from the continental boundary beneath the boat in this diagram. This is the oceanic lithosphere here, the ocean crust basically. And you have a boundary between the continents. And from the analysis I showed you early on, I've highlighted the sweet spot for diamonds. This is the typical depth from which most of the kimberlites appear to be erupting, at least in the compilation for the last 250 million years. The map below is the Kapval Craton in South Africa. This is a kind of an idealized section on the right, but on the left is a sort of a seismic tomography view. This is kind of looking through the Earth and looking at the irregularity of the base of the African lithosphere or crust from below, looking from below to above. And we can see that it's highly irregular and that the roots of the continents are more like an egg carton. I remember that being the way someone described the African region, where the southern African region, where it's highly irregular, the base of the craton. Just finally, in this kind of introductory part, I talked about maybe a sweet spot in terms of the depths that the kimberlites are from. And Sebastian Tapp's 2018 paper was really interesting because it suggests that there may be a sweet spot in time as well, whereby he points out that the mantle potential temperatures were probably too hot earlier in Earth history and would generate major melting. Whereas when the mantle progressively cooled through time, over billions of years, it became progressively cooler, and therefore we favored incipient melting, very low degrees of melting at the base of the lithosphere, and that these melts could feasibly be CO2 and hydrous, CO2-rich and hydrous at the pressures we would expect. So while some people may say that the kimberlite distribution is a preservational artifact because maybe we see more recent ones because we're less likely to have eroded them, it's also been shown that these peaks are probably real when we account for the preservational bias, and that may suggest that there is something to this idea that the Earth has actually become more amenable, I guess, to generate kimberlites through time, which is an interesting and thought-provoking idea. So I've summarized some observations and general points about kimberlites. And another one is that they sample the roots of the lithosphere, the cratonic lithosphere typically. And there were a couple of nice papers that came out in the past few years, which kind of made me think about it. On the right, I guess, to start with the right-hand side, this is a diagram from James Muirhead's paper in Nature, looking at the CO2 release in the East African Rift today. And they kind of point out that there is kind of anomalous carbon degassing from the rift along certain regions. And they tie together lots of observations to show that this carbon appears to be coming from the deep lithosphere, where we have carbonatite metasomatism. And this is if you don't know what that is, it's just a type of kind of, you could view it as a kind of an impregnation of the base of the continent by different fluids, which are typically carbonate bearing, and they may also be water rich as well. And so Muirhead kind of attribute this anomalous degassing to lateral advection, basically convection in the mantle, which then, assimilates this stuff and then leads it to ascend in these melt pockets, I guess, moving through the thinned bit of crust, which is our Rift Valley. And this is also shown numerically on the left by Gorczyk and Gonzalez, where they show that we have very high carbon contents in the roots of these thick regions of lithosphere, and therefore when we have rifting, we're more likely to have lots of carbon forming or at least being released during rifting itself. And I think that's kind of interesting in the context of kimberlites as well, although of course kimberlites tend to be found quite far away from rifts. But that's in itself is an interesting point. We still don't really know what role the breakup of the continents has in kimberlites. Is it just stress transfer, or is it more to it than that? So I went about testing this in this study. So on the left, you can see the frequency of kimberlites over the past billion years. And you can see these are shown here as in green. And in the middle, this is an interesting plot, and I'll take you through this a bit. But this fragmentation proxy, it's basically a quantitative measure of how fragmented the Earth is, the continental plates on the Earth actually are. And so if all of the plates are stuck together, this means they will have a big area, but a fairly low perimeter. So the perimeter area ratio will be low when we have big supercontinents. And I should say that these values are derived from plate tectonic reconstructions. We know how the continents have moved around from paleomagnetism, various other measures, including paleontology even. So we can reconstruct where continents have moved, how they've moved, where they've moved from in the past. And in that sense, we can also figure out how fragmented the continents are. An example is if I take a dinner plate and smash it on the floor, I'm going to generate a lot more perimeter because every little fragment has perimeter. So in a plate reconstruction, as soon as I zip apart these continents, I'll get more and more perimeter, and my value will shoot up. So for the first time, this kind of enables us to quantitatively determine what the relationship is globally between kimberlites and continental fragmentation. And I thought, this is great. This is a great opportunity to do this. But what I was wrong about was that when this value is high, it doesn't necessarily mean that the continents are fragmenting, because, for example, today, we can see at 0 on this plot, the perimeter area is high. It doesn't mean the continents are all breaking apart. So I thought to get around this, what we need is to do a rate of change of this fragmentation, and that's what I show in the bottom. This is just telling us how the rate at which the continents are zipping apart, and that's a much more useful thing to compare with the kimberlites, I guess. And so we do this, and I don't want to go through all the statistics, but we use the kind of what's known as a Bayesian network, which is a statistical framework where we compare two measures through time. And so what we're comparing here is the rate of change of fragmentation of the continents and the Kimberlite eruptions, the magnitude, the number, the frequency of Kimberlite through time. And what we see in this plot is really, really, really interesting, and that's what inspired the rest of the work that I'm about to show you. What we see here is the time lags from negative to positive, and what that means is a zero lag on this is the point of continental breakup globally, and the negative values suggest things that have happened after breakup. And so we're seeing that the correlation between Kimberlites and breakup seems to peak globally after the point of continental breakup. And you can see that it happens at around 25 to 30 million years, or actually minus 26 million years after breakup. And this correlation increases to about 0.55 or 0.6 when we deliberately target the more recent Kimberlites, 250 million years of Kimberlites, when our accuracy, I guess our uncertainty of plate tectonic reconstructions is much lower. So that gives us confidence this is a real peak. And also when we look at a billion years, this is the past 500 million years, by the way, when we look at a billion years of Kimberlites, we get exactly the same lag and a similar correlation. So it tells us that there's something statistically significant. It's telling us the continental fragmentation predominantly, not exclusively, because you can see some Kimberlites erupting before breakup, but you can see that predominantly globally, fragmentation of plates leads Kimberlite magmatism. That's really interesting. So we thought, oh, how about we do the same for large igneous provinces? Because as you can recall from earlier, I suggested that they have been proposed. I guess they are the surface expression of these plumes, these super plumes, if you like. The large igneous provinces themselves are the surface manifestation of those. This is the volcanism at the surface, which is fed by plumes. And so we do exactly the same analysis with the degree of the rate of fragmentation and the large igneous province volcanoes. And we see a different relationship. We see that most of the large igneous provinces seem to occur before breakup. And so that tells us the other thing is the correlation is very weak, relatively weak compared to the Kimberlites. So that tells us that plumes largely predate breakup and long predate Kimberlites, typically globally by about 30 or 40 million years, suggesting that maybe they're less directly linked, Kimberlites that is, are less directly linked to these large igneous provinces or plume volcanism. And the other interesting observation from the Cretaceous, for example, the Kimberlite corridor in North America, which you'll be familiar with, as Bruce Kjaersgaard and people have pointed out, it's quite far from any known plume influence. And that's always been a bit of a kind of an anomaly as well, and something that's been hard to understand. And the other observation, which has been coming together, I guess, in the last few years from Giuliani's work, is that Kimberlite geochemistry, and Sebastian Tapp has done a lot of work as well, showing that a lot of Kimberlites geochemically are inconsistent with plume involvement, even in areas where they're quite close in time and space to plumes. And instead, their data suggests that Kimberlites are related to partial melting of the convective mantle or the mantle-asthenosphere, coupled with assimilation of cratonic lithosphere, which may be wet, and that would be consistent with Bruce Kjaersgaard's model for the Cretaceous Kimberlite corridor. So most people are a little bit skeptical when they see global data analyses and when you're using like machine learning. So what we did next was we scrutinized this further by looking at the spatial and temporal relationships between Kimberlites and continental plate margins at a regional scale, targeting, I guess, plate tectonic reconstructions for well-studied places. So initially we did this in Southern Africa, and then progressively we added more and more as reviewers required. We studied South America, and then we also studied North America. And what we find is quite interesting and quite startling. When we kind of forensically unpick the spatial relationships and the temporal relationships between kimberlites and the big rifts that allowed these continents to break apart, we see that the kimberlites appear to migrate. And you can see this isn't clean. It's not like a one-to-one relationship. But in most cases, we see that the kimberlites appear to migrate further away from the rift margins over time. And there are obviously a few exceptions to this. But predominantly, we can see that they migrate. And we can even determine from the slope of this regression that the migration rate is about 16 kilometers per million years. And what's also interesting is that both in South America, I should say, and Africa, these are the plots here showing the frequency over time, this time lag relative to breakup, continental breakup. We can see that both of these distributions show a peak at around the point of breakup, and then a bigger peak at about 25 to 50 million years. And this is consistent with the peak that we see in the global analysis. And that was sort of an exploratory analysis. We then look at, because we realized in doing this work that the kimberlites also appear to be migrating from rifts as well as the point of like breakup itself. So obviously, when we form a rift, that's the kind of protracted period when we're starting to stretch a continent. It eventually ruptures, just like stretching a bar of toffee. It will eventually break. And so that generates potentially two interesting phases whereby we can, and I'll come to this a little bit later on, we can actually influence what's going on in the mantle in two different steps, because we have rifting and we have breakup, two different processes related obviously in time. And what we see is kind of interesting that on average, when we look at each continent, when we do this analysis, we see that the migration rates that I showed you before appear to be quite consistent on the different continents, Africa, North America, and South America. They're in and around 18 kilometers per million years, which is quite similar to this example. And in some cases, a bit higher, about 26 kilometers per million years. So that's interesting. And I mentioned these two peaks that we saw in South America and Africa. But interestingly, when we look at North America, we also get two peaks. We get an early peak before breakup, and we get the later peak, which these two peaks seem to mirror what's going on in Africa and South America. But the difference is the timescales. When we started to break America up first at the onset of Pangea breakup, starting about 240 million years ago, that was quite hard. The Earth struggled to get going because it's much harder when you have an entire landmass. It's harder to get the kickstart and get things moving. And so the time it took between rifting and breakup in North America was much longer. It was about 76 million years. Whereas in South America and Africa, Southern Africa, the time was less than that. It was less than about 40, 50 million years. So for that reason, the timing of the first peak is slightly different in North America. I think this is basically lagging the onset of rifting at about 76 million years before breakup, and in that case. And that's an important observation. So motivated by these observations, and I really couldn't explain why we were seeing this migration trend. It's very difficult to explain that kind of trend using plumes, which would traditionally be attributed to migrating trends. And that's partly because if you look at the regional clusters, you see that the plumes are moving the other way. As soon as we split Africa and South America, the plumes actually move offshore and produce Walvis Ridge and the equivalent on the South American side. So plumes don't migrate to the areas of thicker lithosphere. So there was a big period of head scratching, wondering what is it that's driving this migration trend. So I kind of, a lot of intervening time passed since making this first observation. And I assembled a team, actually assembled two teams, one of them led by Sascha Brun in Potsdam, who is an expert at thermomechanical modeling. And just to explain that to people who aren't familiar with it, that's just generating a model of the crust of the lithosphere and the mantle in terms of reconstructing the properties of viscosity and the strength, like diffusion creep. There's so many parameters that go into these models. They're quite accurate. And so Sasha has worked a lot on rifting, and I thought it would be good to involve him and try to figure out what we can understand about the nature of rifting. And we also undertook a scaling analysis, which is basically using kind of mathematical models of instabilities in the mantle, representing the boundary layer that we get between the rigid lithosphere I talked about and the convecting mantle. And so what you can see in these models, firstly, is that when we form this rift, we completely influence the flow pattern, the convection beneath the rift. And that happens for a number of reasons. The first thing is when we stretch the continents here on the left and A, you can see that you form space. So you're opening up space. And when you open up space in the mantle, you have an upflow, quite a rapid upflow of weak, hot asthenosphere. And because the lithosphere is relatively cold, at least compared to the asthenosphere, you then set up a gradient, a temperature gradient horizontally, whereby this hot stuff, this flushing up, meets the cold stuff. And as it meets the cold stuff, as you know from when you're cooking in a pan, it starts to cool down. And as it cools down, it becomes more viscous and it becomes more dense. And then it basically settles, it sinks. And that's what generates this circulation pattern. This is called edge-driven convection. And that's the basis of what's happening here. But what we saw in the models was amazing. It was that when you set up one of these, what's known as a Rayleigh-Taylor instability, you've probably seen similar things in a lava lamp. If you've ever seen a lava lamp where the fluids kind of rise and then they reach a critical density and they sink, or viscosity increases, they sink. And this happens really abruptly. We were seeing exactly the same things in our model here. And what was amazing was that when you set this up, this cell, it influences the region further downstream. And we end up with what I would describe as a domino effect, whereby we form second generation and third generation convective instabilities that migrate with time further away from the continental boundary. And this is kind of cool because it gives us a possible mechanism to test whereby maybe this is explaining the migration of Kimberlite volcanism through time in a crude sense away from the rifted margin. And also what's interesting is in our models, and both types of models showed that the scale of these instabilities should be on the order of 50 to 100 kilometers in diameter, which, as you'll recall, is remarkably similar to the scale of Kimberlite clusters at the surface. So there may be a link there to consider later on. That's all very theoretical. I want to show you that model and how this is basically a model showing us what happens in the mantle as we stretch the continent, as we did in South Africa and South America in the Cretaceous. This is the green is the lithosphere, the gray at the top is the crust. At the base here is the mantle convective asthenosphere. And the beige layer is our cratonic keel. This is basically the thermal boundary layer between the rigid lithosphere and the hot asthenosphere. It's a kind of transitional boundary layer. And what you can see now is these instabilities and how they propagate with time. And you can see as they propagate, they form this quite strong upwelling. And that's another important point. I should say that these clearly propagate further away from the rift towards the cratonic interior. So they're ripping along the base of the continents into the interiors of the continents. And they're driven, actually, in our models, they're driven purely by a density contrast between the colder lithosphere and the hotter asthenosphere. This may, of course, also be augmented by metasomatism, and that's the infiltration of fluids, which can make this basal layer more dense or less dense through time. And the other important thing, if I can just play that simulation again, is that the removal of this thermal boundary layer is causing thinning of the lithosphere. And we can see the convective downwelling. So as we're dragging down the beige stuff, we have to balance that by upwelling of the low density hot asthenosphere. And of course, if you're having upwelling of hot stuff, that could potentially cause partial melting. It could cause decompression or partial melting. And that was something that kind of dawned on us that could be important in the context of Kimberlites. Just a point to make, and conscious time is moving on, but another important observation that we make using xenoliths from Kimberlites, and we use this analysis of Mather et al. Geotherm analysis, and it effectively just uses these geotherms to figure out or calculate the thickness of the thermal boundary layer, shown in pink. And I don't want to dwell on this too much, but just to show you that globally, the thermal boundary layer is very uniform. The thickness is around 33 to 35 kilometers on average. And that's important. And I think in the context of our observations of Kimberlites, the migration appearing to be consistent between continents, we figured that the mechanism, if you like, that generates these must be kind of, it's not reliant on some quirk of locally what's going on, although that may come into play. It's telling us that there's some fundamental physical mechanism, you know, that happens when we break continents up. It's not just the kind of random event. It's something that's highly organized, highly sequential, and something that may remove this thermal boundary layer, just as our models show, because that's the viscous fluid, you know. So we did lots of calculations, and I'm not going to dwell on this too much, but our calculations basically tell us that the migration rates for these fluids, if we consider all these different fluids, viscosities, for example, in the mantle, the migration rates that we get from these calculations are on the order of 14 to 26 kilometers per million years. And the geodynamic models that you've just watched, they are completely independent of these calculations, and they give us migration rates for the instabilities of about 15 to 20 kilometers per million years. And if I can just draw your attention back to the Kimberlites themselves, the migration rates of those was typically around 16 to 18 kilometers, but globally on the order of 18 to 26 kilometers. So we can see that the migration rates of our Kimberlites match quite well the expectations of, you know, what the rate of migration of these instabilities should be through time. But I guess the question is, what is it then that's happening at depth when this is all happening? And that took a while to kind of figure out, because I was kind of thinking about it from the wrong angle. And I realized actually what we need to do is consider when this instability, let's say, assuming we're right about this, if it does rip beneath the continent, it's going to, as it moves, it's going to come into contact with peridotites and form partial melting of peridotites, of carbonate-bearing peridotites. So we looked at the phase relationships here. This is a phase diagram for carbonate-bearing peridotites. And we can see that in the conditions shown in this red box on the left, this is really nice. The conditions that I showed you for the thermal boundary layer, which I said was globally quite uniform in terms of the thickness and depth and so on, pressure and temperature that we can reconstruct. We see that that boundary layer that we're proposing here, and this, you can see the snapshot from the model, we're proposing that's been ripped away. Given these phase relationships, that should contain low degree hydrosilicate melts at the higher temperature end, and it should also contain carbonate-rich silicate melts. And there was a really nice paper by Jeanette Pinter in 2022 showing that hybridization of these kind of domains is capable of generating Kimberlites, melts of Kimberlite composition. But what we were lacking was a mechanism to bring these together somehow. And what we're proposing is that these compositions are hybridized or mixed as we rip the thermal boundary layer off, drag it down, and we have asthenosphere upwelling. We've shown mathematically that this upwelling should be adiabatic, and by that I mean that it doesn't lose temperature as it rises. So we remain hot, and those hot upwelling melts can basically interact and mix and assimilate the downgoing lithosphere keel, which is going down. Not only that, we actually show that given the properties of the mantle, we show that the degree of melting that we would expect to generate by this process is about 1% or less. And that's remarkably similar to degrees of melting that people think Kimberlites have undergone based on petrology and other dynamical constraints. We also show that this process should generate melt productivities. This is a bit of a weird value or a range or quantity, I should say, but it corresponds to hundreds of cubic kilometers, which is kind of similar to what we would expect in a kimberlite cluster, where we have lots of pipes. And we also show that the melts that we would expect to generate by this process should be water bearing. They should actually be very high in water, containing over 10% water, which is kind of remarkably similar to estimates from Steve Sparks's research. So that's kind of interesting. Just very briefly, what's really interesting as well is that we have evidence in Southern Africa for an abrupt change in lithospheric thickness, going from group 2 kimberlites to group 1 kimberlites. These are known as lamproites. These are more lithospheric rich. And then later on, our kimberlites contain more asthenosphere. So it's perhaps showing us that this process is ripping lots of lithosphere at the beginning, and over time, as it removes the keel, we have more upwelling of hot asthenosphere, and we have stronger asthenospheric signatures in our kimberlites. And that appears to be the case for lots of different proxies here. Is that a quirk? We looked in North America as well, and we see exactly the same kind of trend happening, where we go from lithospheric rich kimberlites to these more asthenospheric rich kimberlites, which may signify progressive convective erosion of the lithosphere through time, and the migration of those instabilities, allowing the kind of migration of kimberlite magmatism, the locus of kimberlite magmatism through time. So we get low degree partial melting. What's also interesting is once this thing has passed by, if you imagine like a train moving past, there's still going to be a little bit of upwelling afterwards, and that may produce very low degree melts. It may even refertilize the keel. We may have some of the stuff that's stripped away coming back up and producing very low degree melts. They may not be enough to erupt, but they may actually somatize the keel. In the interest of time, I'm just going to say there was a recent paper that showed that maybe this kind of process is also happening in Australia prior to 1 billion years ago, which is kind of interesting. This paper on Argyll showed that the kimberlites erupted around the time when this supercontinent broke up, which was kind of an unexpected finding. But it seems to be, this one example seems to be consistent with the global picture that we are suggesting. I'm actually, because we're low on time, I've kind of already said all of this with the conclusions. I'm keen to show you, just to conclude, an animation which we produce, and it's not just a video showing you the kimberlites erupting through time, but it's also making them into music. And we figured it would be a nice way of showing the kimberlites appearing through time. So what you're going to hear is a note for every kimberlite, and the pitch of the note that you hear is set by the paleolatitude where it's erupting. So if something that's really high pitch will be erupting in Canada probably, or in Siberia, whereas the low pitches will be in the southern hemisphere. And the stereo sound, so whether you're hearing it on the left or the right in your headphones, is the paleo longitude, you know, whether it's forming in the west or the east. And you're also going to hear the sound of the continents breaking apart, which is the sustained bright and dark sounds in the background. So I'm going to now play this animation just to show you the music of kimberlites as they're erupting with the plate cycle. Thank you very much. That's the talk, and if anyone has any questions, I'm happy to answer them.
Thank you, Tom. That was an excellent presentation. I loved your
Amy.
video at the end. I feel like I was just at the spa. Very soothing. So now we're going to get started with the Q&A portion. So if anyone has anything that they'd like to ask, you can either ask it directly or send it through the chat. I will go ahead and get things started because I have a question of my own. You had touched on stuff going on in the East African Rift, and obviously there's lots of carbonatite magmatism there right now, and some recent kimberlite, maybe kimberlite deposits there. Is that an area then that you would? I'm not going to open that can of worms.
Yeah, no.
But is that an area that you think that we should be potentially looking for modern day kimberlite volcanism?
Yeah, I mean, you probably noticed in the animation, you know, the sounds were coming from Africa. You know, they were coming from the vicinity of the East African Rift. And, you know, whether or not you decide these are kimberlites or not, they are weird. And, you know, most of you who work on kimberlites know there's a whole plethora of weird and wonderful compositions, particularly that happen early on, you know, the what we would call traditionally as group 2 kimberlites. So you got lamproites, orangites, you know, all these range of rocks. So whether or not they are kimberlites strictly isn't really relevant to the question, which is, could these be caused by the rift? And I think they absolutely could, because our model shows how rifting reorganizes mantle flow. And that's not just something that's confined. I think we think of mantle convection and we think it's confined to the mantle. But I think what we've shown is that it has ramifications for what's going on at the base of the continents. And, you know, it's no coincidence that lots of our kimberlites, when we look at the depths of the thickness of the lithosphere they're all from a very tight range, which defines, you know, where most of the lithosphere-asthenosphere boundaries are. What I'm trying to say is that this stuff that's going on in the mantle is disrupting the roots of the continents, and that can instigate quite near to the rifts. And in the animation you saw, the kimberlites that we're seeing in the recent past geologically are quite near to the East African Rift, right down as far as Tanzania. So absolutely, you know, there may be lots of unexplored, unknown kimberlites or related rocks beneath some of the regions adjacent to this area. And a prediction of our model would be that they are a bit weird, because we've shown that early on the kimberlites should contain more should show evidence for more lithospheric assimilation, which tends to form these weird phlogopite-rich, you know, varieties of kimberlites and other rocks. So yeah, certainly an area that would be interesting to look in a bit more. And the question is, you know, how do they relate specifically to the rifting? We're learning more and more about the geodynamics of rifting over the past tens of millions of years in this area. So it's definitely worth revisiting. And I think it's a great question. Thank you, Amy.
Thank you. Does anyone else have anything they'd like to ask?
Yes. Since you've been looking at rifts, and alkaline and carbonatites are related to rifts, have you looked at those, thinking about looking at those? Any relationship you'd like to speculate on?
Yeah, I am. Thank you for your question, Michael. I've definitely thought about them. I mean, as you know, there's kind of a spectrum. Some people may disagree, but it's kind of a spectrum between carbonatites and kimberlites. We certainly see some kimberlites which appear to be very closely related to carbonatites. So one might agree that there's some kind of genetic relationship in how they form as well. And the question, have I looked at them? I've not applied the same approach. And that's partly because it's a tricky old thing, because as you know, carbonatites are in some ways quite complex because there are lots of different types. There's some that are people would describe as magmatic, and that would be great if we had a compilation just magmatic ones, or mantle, from the mantle. Whereas there's lots of other ones which, seem to form around other intrusions related to maybe different crustal assimilation processes. So it's not easy to compare like with carbonatites. I'm certainly open to working on them. If people want to collaborate on this or have data, then I'd certainly be interested in applying the same kind of statistical approach to understand the links of them, even to Kimberlites. I think Steve Foley's work has shown that there's quite a systematic zonation where you seem to have carbonatites closer to continental boundaries. Maybe that's because they like thinner lithosphere, where it's been stretched. It's not saying we don't get carbonatites in the further away from those places, but generally when you look at maps of carbonatites, they tend to be heavily clustered very near to the continental boundaries. Thank you, Michael. I hope that answered your question.
Yeah, I'd just like to make a quick comment. I was sort of suggesting that I like your approach, and I was just thinking taking your approach to the carbonatite alkaline suite may be useful.
Yeah, really useful. Thank you. I'm very open to chatting to you about that another time if you want. Thank you, Michael. Excellent.
It looks like Evan Smith has his hand raised, so go ahead, Evan.
Yeah, can you hear me okay?
Yep.
Yes, excellent.
Great presentation. I really enjoyed the paper. And one of the things I was hoping you could comment on is sheared peridotite xenoliths, and whether or not you think that might be somehow evidence of local convective instabilities.
Yeah, I'm really glad you raised this question. And I was talking to Emma Tomlinson. I gave a similar talk in Dublin a few days ago, and she asked a similar question, Evan. Thank you. I did think about this because when you think about it, it makes a lot of sense. If you're taking the very hottest bit of the keel and dragging it down, it should generate shearing. My understanding is that the shear rates that have been constrained, I think there was a paper by Schema and Carato where they looked at the rates at which they think this shearing happens. And it's believed to be very fast. And I compared those rates that they've constrained. I couldn't tell you off the top of my head what they are because it's a very large the number's something to the 10 to the 15 or something. But the shear rates are very high, which suggests that it happened very abruptly. We don't know. I mean, from our thermomechanical simulations, the shear rates that we expect, I guess, in these convective instabilities are slower than the rates constrained for these sheared peridotites, which is why I didn't really go into it in any more detail. I wouldn't rule it out because the uncertainties on some of these constraints for xenoliths are very high. It's feasible, that the and maybe more work can be done on this, but it is certainly feasible that they're generated by it. But my instinct is that these sheared fabrics form too quickly, and they may therefore be more related to the intrinsic ascent and eruption of the melts as they kind of communicate with their surroundings as they're rising through the lithosphere. I would like to think that these sheared fabrics might be related to the instabilities as they sink, because our models, may underestimate the rate at which these things sink, because once it becomes viscous and dense, which we think happens, it can happen really, really abruptly, maybe more so than the models show. So a part of me wants to believe that they could be connected in some way, and I'd certainly be interested in following that conversation up with you at some point. Hopefully that answers your question, Evan. Thank you. Thank you for the question. It was really good, and I'm glad you brought it up because I forgot to mention shared lertzolites.
Okay, we do have a question in the chat here from Jonathan Clark. He says, great presentation. My question is, Rayleigh-Taylor instability blobs have a characteristic radius relating to the viscosity and density of the two fluids in question. Have you compared the real radius and mantle properties with your model?
Yeah, so we, as I mentioned earlier on when I was setting up those things, we actually, the way the study worked was I contacted two modelers, to get some help with this side of the study. One of them was Sasha Brun, who did those simulations. The other was Steve Jones. They're very different people. Sasha does stuff with the thermomechanical simulations, and they are clearly very sophisticated in 3 dimensions and so on. And you can run them, you can change the properties and rerun them and so on. The other one, the analytical models, we considered about 6 different fluids, which we believed were, from other constraints about the mantle, were pretty much representative of, the densities and viscosities of the thermal boundary layer, but also the asthenosphere. And obviously that's a highly debated topic. It's impossible to pick a number out of the air and say that's what it is. So that's why we did 6 different fluids. But the 3 or 4 fluids that we thought were the best guide, I guess, or the most realistic, ended up being very similar in terms of the characteristic scale of the instabilities that you mentioned are related to the viscosities of the fluids. They were very similar to what the thermomechanical simulations were showing. They were on the order of between 40 and 70 kilometers in diameter, which is more or less squarely in line with the scale of the Kimberlite clusters, but also the suggested footprint in the mantle of melting that generates these Kimberlites at the surface. So yes, I guess we deliberately tackled the problem. Well, actually, I should be honest with you. I didn't think that both modelers would do the work. And initially they didn't even know about each other, because I thought it'd be kind of nice for them to do it independently and then come together. This was all during COVID, so I had an excuse, we couldn't meet up and so on. So we met on Zoom. And it was kind of a jaw-dropping moment when they came together and they showed the same thing in different ways, not knowing about each other, using completely different approaches, and also considering completely, different scenarios. But the net result was the same, which kind of gives you confidence that, there's something going on here it's just intuitively right, and it fits remarkably. When we met, they didn't know about the Kimberlite migration rates. So when we all compared our rates and they were all the same, we were like, yes, this is actually almost too good to be true. And that's when, of course, you start to attempt to try to kill the model, so can we disprove it? Can we find evidence where maybe it doesn't work so well? Is there evidence in the rock record that this is actually happening? Because we're geologists, we like to find evidence for these kind of mechanisms when we think we know what's going on. And that's why it was nice to see evidence for similar sort of removal of the root happening quite abruptly. I am kind of moving a little bit off topic here, but yeah, to answer your question, we think we've tackled that quite comprehensively by the way we did the study in the first place. Thank you for the question, and feel free to chip in if you've got any more.
Thanks, Tom. Does anyone else have anything they want to ask or add? Hi, did you have a question?
Yes. Yeah, thanks for the presentation, Thomas. Amazing sound video at the end. So I just want to comment, what's the thing that is astonishing for me in your modeling is that migration and propagation of that Kimberlitic fluids or asthenospheric related processes that eventually will cause Kimberlites to form and erupt is dependent. That process is dependent on the removal of the thermal boundary layer. and dependent on the metasomatism in the lower part of the lithosphere. So do you see it the same way? So if you do not have that removal of the thermal boundary layer, you cannot rotate and move the fluids further?
Thank you. Maya, that's a really good question. I think, yes, it helps to remove some, because when you set these things up, you saw it's like a chain reaction, as they propagate, you get first, second, third generation. I think what we saw was that the earlier instabilities weren't capable of completely removing the instability, the thermal boundary layer. And successive ones, because you had already removed some, successive ones didn't require as much work, I guess, to completely remove the boundary layer. But what we're seeing, I guess what we can tell from the simulations is that we don't need to completely remove this thing. And that's kind of a fundamental part of the model, that we see that we can generate Kimberlites, but they're just much more lithospheric early on, when we maybe we disrupt a little bit of the thermal boundary layer near the base. And when we completely remove the thermal boundary layer, we may expect to see more group 1 type Kimberlites. That is a little bit dependent, I think, on the metasomatic history of the keel. As you know, metasomatism is a complex multi-phase process. We see signatures in Kimberlites which are billions of years old isotopically. But we also see that there's evidence in a lot of cases, not all, we do see evidence that there is metasomatism not long before eruption of the Kimberlites. We see often there's a phase that's, quite close in time, in the millions of years building up to the Kimberlite magmatism. We certainly see that in Southern Africa, and I was reading today a paper on Canada. I can't remember the exact Kimberlite, but diamond inclusions telling us that there's a pre-eruptive metasomatism. And I do wonder if maybe these early instabilities that aren't capable of removing the keel may actually be metasomatizing themselves in redistributing stuff that it's removing locally, as we have upwelling. And as I mentioned, if you have very weak upwelling, you may have very, very low degree melts, which aren't capable of erupting, but may infiltrate the keel and locally metasomatize and possibly even increase the density of the keel, which can be it can be self-perpetuating, because that can increase the density and that can also destabilize the root. So yeah, I think it's highly dependent. As you know, if you get a map, you don't get like Kimberlites uniform. It would be great for exploration if they were uniformly distributed across the Earth's surface, but clearly they're a function of the ingredients. You need the right ingredients in the right places. And your question is hinting to that, whereby it may be locally that you have just the right conditions to have the right kind of metasomatic history, for example, to have the right ingredients to generate Kimberlites in the first place. So it was hopefully that answers your question. It was a good question, and certainly one that I pondered for a long time, and still details of that metasomatism are still unclear to me, but I think it's coming together a bit. Thank you, Maya.
Looks like Herman has a question here. Go ahead, Herman.
Yes, good talk. Thanks, Tom.
Thank you, Herman.
I just wanted to pick up on the latest discussion, the one the question you answered with Maya.
Yeah.
And that relates to the timing of when you see the asthenospheric imprint.
Yeah.
And when you start seeing mixing with lithospheric imprints.
Yeah.
And I've got some evidence which is exactly opposite to what you've just explained, and I'd like to share that with, if I can share my screen. Amy, if you can switch that on.
It should let you share.
Oh, maybe I'm still sharing. So if I unshare, oh no, don't show I'm
no,
sharing.
I think
I'm not sharing
Herman,
anymore.
if you just click share screen, it should let you.
Yeah, let me just find it here. choose. Okay, so yeah, share screen. Okay. And I want to share this paper. So a lot of this stuff has to do with timing of kimberlites, right?
This is Jurassic Kimberlites in Baffin Island, okay.
All of these things that you talk, rates of eruption, rates of magma accumulation, rates of progression of kimberlite melt through through space. It all is dependent on the age data set, and you're using the Tupper data set, which is a good compilation. But one of the things that I've been doing through my career is systematically trying to date individual kimberlites with accuracy inside a kimberlite province, and I've only achieved that twice.
Yeah.
And the latest version of that is this Chidliak kimberlite province, and by collaborating with a top-notch guy like Larry Heeman, we ended up with a fairly unique data set.
Yeah.
And it's an isotopic and age dating data set based on perovskite dating. I'm not going to give you, here's the paper. It's been published for a long time, for quite a while. I'm not going to take you through all the intricacies, but essentially, if I can just get down to that figure at the back here, there's all the data. Essentially, the summary diagram that we need to consider for this conversation is this one over here. It's figure 6.
Okay. Yeah.
Let me just make that a bit larger if I can find the right button. No, I can't find that hidden. Let me just move something away here, move this away somewhere. Here we go. I can make it bigger over there. Okay, so this is the, this is your standard epsilon strontium neodymium diagram. In this case, we've got, the global sort of reference data set, and in yellow, the data from Chidliak.
Right.
So we discovered 74 kimberlites. We dated about half of them, and also got the isotopic compositions.
Yeah.
What you see here are two arrows in time.
Yeah.
The initial kimberlites, the earliest or the oldest kimberlites that erupted in this field, erupted basically at the red dot, which is asthenosphere, pure asthenosphere for a group 1 kimberlite. So the earliest melts we see in the Chidliak kimberlite field are, they are essentially asthenospheric isotopic signatures.
Yeah.
And then you see a progression, which is, it takes about 17 million years, in two directions, whereby an asthenospheric and intrinsically asthenospheric melt is being contaminated with crustal isotopic signature or metasomatic mantle isotopic signatures. And there are two arrows, interestingly enough, at Chidliak. And both arrows point to known metasomatic resources or reserves that are, also in the deep lithospheric root, and that have been there for a long time. Yep. And so what this tells us is that by the time an asthenospheric incursion, let's call it an asthenospheric incursion, produces a melt, then that melt, all of these melts have diamonds in them, so they are high pressure melts by definition. Then that melt starts off as asthenospheric, and then as that thermal welt, if you want, expands with time, whether that be by conductive mechanisms or by actual ripping off the base of the thermal boundary layer. Not sure how that, which of these two mechanisms is ongoing. Then that asthenospheric melt then starts being contaminated with the surrounding lithospheric materials.
Yeah.
So it's a slightly different progression, but it's got the same elements in it.
Thank you, Herman, for pointing that out. It'd be good to see the age, what the ages are in that plot.
Yeah, we can. I'll show that to you. That's figure 4 and 5. I'll show that to you in a moment. The point I'm trying to make is this: there are too few studies of this nature that are coming out. People are aggregating individual data points for venture, for this and for that and for the other thing.
Yeah.
Nobody is systematically investigating trends with time in melt composition within a single kimberlite province.
Yeah.
And it's once you start doing these kind of studies that you start finding the answers to the mechanisms that are involved.
Yeah.
So let's just go back to the earlier.
No, Herman, I completely agree with what you're saying, and in some ways, we're kind of, you know, we're presenting a global model, and as much as anything, it's to make people think about stuff like this.
Sure.
I mean, it's hugely important because you kind of need, you know, you obviously need good ages of these Kimberlites. And I think one thing we proposed in the paper towards the end is, you know, how do you test this model? The clear thing is exactly what you're saying. It's going to clusters and seeing how the compositions change through time. What I would say is you need to take on board all the context. I mean, I would say, I mean, these Kimberlites look like they have the similar age range to the Greenland Kimberlites from Nuuk, is that right? The ones
So the Greenland, there is one Kimberlite that's got a younger age in Greenland. Yeah. Greenland, the ages are sort of 500 to 550. These are much younger.
There's some though, aren't there, in that Sebastian's published on around Nuuk, which are Jurassic.
Yes, there is one or two.
There's a cluster, I think 166 to 157 million years. So similar-ish to yours.
Yeah.
And actually, interestingly, a similar distance to the rifts. If you assume that our model is correct for these, the main rift that they would be related to would be quite far away. In the kind of Central Atlantic, the northeastern part of the Central Atlantic.
So this is literally, Chitliak is on the western flank of the same rift that would have where Greenland is on the eastern flank. So Chitliak is on the northeast coast of Baffin Island.
Yeah.
You asked, I mean, you can look this up yourself. You asked what the age range, and this is the diagram that sort of summarized the trends of isotopic compositions with time, and the age range is about 157 to about 140 million years, 17 million years.
Yeah, I think in my talk, you know, I was painting it as a black and white thing, but I think when you look at the models, you know, if you look at the thermal boundary layer as a lava lamp, you know, you get stuff dripping down. You know, initially your melts are going to have stronger asthenosphere, because it's as this stuff drips down like a blob, you're going to have upwelling, and that may generate stronger asthenospheric signatures. So it may take time basically for that stuff that's dripping down to be assimilated, or the upwelling to actually carry it up. We figured that it will be a few million years potentially. So you're not necessarily going to see a simple trend, but you may see a trend that goes in the opposite direction to what you're expecting. And I think it sounds like special pleading, but I do think that it's more complicated how this process unfolds, because it involves fluids, and fluids are, when we have this kind of segregation, it can take a while, you know, for the assimilation to basically be manifested at the surface, you know. So I completely agree with your points, and I think it's imperative to go and actually look at these clusters and date things as well as we can. I mean, you mentioned TAP's database is pretty good, but we supplemented it with new dates, and we also did uncertainty analysis with what we did. So we took the age uncertainties as well in our analysis to make sure it was like as robust as possible. So I guess that's how we went about tackling the problem.
So I just wanted to also point to another paper that was published, which I was fortunately involved, which is a spin-off of a dating paper.
Yeah.
And that was for the Ecadic Kimberlites.
Right.
I'll just flick over here.
Did you say Ekati?
Yeah, the Ecadic Kimberlites. So this is Grant Lockhart was the geophysicist, and myself and John Carlson were involved. it's a companion paper to another paper where Rob Creaser was the lead author, which is phlogopite dating of the Ecarte Kimberlites, in which we showed there are 4 episodes of eruption. And it's become quite a classic paper from that point of view. What a lot of people haven't realized is there's this companion paper which did this. We compared the age dates and the magnetic moment captured during cooling of each kimberlite with the magnetic moment in seafloor striping. So in other words, we got a connection between the cooling of a particular kimberlite at the Ecarte property with the piece of the globe that was recording that same magnetostratigraphic information at the time. What that correlation looked like. So here's all the age dates. There's all the kimberlites. We found that there were different magnetic moments in time. In other words, the Earth's remnant pole was moving at the time by deconvolution. Here's the magnetic striping that we could, and the errors of the different eruptive episodes. For instance, that age correlates with that normal cron, C27. It's in black, the white ages and the errors and so on. We got some pretty good correlations. We were actually quite amazed that we were even able to do that. What was most amazing and did not appear in this paper is that the only piece of seafloor that recorded the same crons as the cooling of the kimberlite magmas at Ecarte is in the northwestern Atlantic, between Greenland and basically eastern Canada. That was the only piece of tectonic activity where rifting was progressing to the extent that it recorded seafloor striping. It's recorded in no other piece of seafloor striping, and it turns out that piece of seafloor is 90 degrees on a great circle relative to the trends that we see in extension on the Ecarte property.
That's interesting.
In our brain, that meant that far-field stresses were determining the eruption centers on the central slave. That's basically what that boils down to as a result of that correlation. And we say that in a fairly cryptic way at the front end of this paper. Somewhere in here. Here we go. The location and orientation of the corridors of interest appear to be largely unrelated to basement geology and show evidence of rotation with time that speculatively could be linked to far-field tectonic stresses. It's essentially opening of an ocean basin like 700 kilometers away on the Great Circle. So,
really
again,
interesting. Thank you.
Again, it's just a function of having dated a lot of kimberlites in one location. You can start pulling apart some of the cause and effect situations.
Yeah, that's cool that you're locking in the magnetic field.
All right. That's
great.
all
Thank you,
I
Herman.
Thank you.
Much appreciated. Great to have you here.
Thanks, Herman. Does anyone else have anything that they'd like to ask before we wrap up here?
I've got something. This is Jonathan. The animation at the end, is that available anywhere? Because I'd really like to rewatch it a few times and make a mental note of certain details.
Yes, I will. It's on YouTube. So yeah, it's accessible. I will put it in the chat so you can watch it, and it's quite soothing, isn't it? So you can watch that at any time and kind of play it as my screensaver. There is some artistic license. We obviously removed a lot of detail, so I would, if you're actually interested in the technical detail of the rifts and so on, I would direct you to the paper, because we have all the data available online as in the supplement to that paper. And if you've struggled to access it, just drop me a line. But it is all freely available. And this animation is kind of simplifying it, so that, because people like it to, you know, obviously for showing an animation, it's much easier when there's not loads of detail. Did you see that? So there, I just sent the YouTube link in the chat. Were you able to get that, Jonathan?
Yep, I see it. Thank you.
Great.
I'll be bookmarking that shortly.
Excellent. And I forgot to say that that was made by some Canadians, my friends at System Sounds in Toronto. So they're excellent to work with. They do stuff with NASA, but I knew them from something else. But they're great guys and amazing at what they do.
Very
Thank
cool.
you, Jonathan. Thank you, Amy.
No problem. No one has any last minute questions before we wrap up? Doesn't look like it. Okay, well, thank you very much, Tom. That was an excellent, excellent talk. And we will be putting this up on YouTube as well on the VKC channel. If anyone couldn't make it or wants to watch it again, it will be up there in the next couple of days. So enjoy the rest of your night, Tom, and everyone can get back from their lunch breaks now.
Excellent. Thank you so much, everyone, for coming. And it's been lovely to talk to you.
Thanks, everyone. Bye-bye.
Thank you. Bye.